là.
Ah non?
Ça vous dérange pas si j'enlève mon masque juste pour que ce soit plus audible pour les gens qui sont.
Ah non?
Juste enlever mon masque pour que ce soit audible pour les gens qui sont. Je sais pas, je demande juste.
Bonjour, salut, pas de problème. Il est parti plus tard que prévu.
Alors, je crois qu'on m'entend pas très bien a priori. Faut que j'essaie de corriger ça. C'est toujours un peu relou. Ok. Ok.
Donc c'est 45 minutes, hein, c'est ça?
C'est ça.
Donc, monsieur Ramzi, vous avez 45 minutes pour vous présenter vos travaux de recherche et cette séance sera suivie par une question.
Très bien. Merci beaucoup. So, hi everyone. My name is Zachary Ramzi. I'm a PhD student working under the supervision of Philippe Soussiou and Jean-Luc Stark. And today, I'm going to present the work that I did in the INRIA parietal team and at Eurospin and Cosmostat during my PhD thesis, which is entitled Advanced Deep Neural Network for MRI Image Reconstruction from Highly Undersampled Data in Challenging Acquisition Settings. So what you've just heard is what you would hear if you were to undergo an MRI. On top of that, you have to lie still in a confined space. Let me tell you that it's not going to be the best time of your life. And so you can see here the photo of a person who's undergoing such an MRI, and you can picture yourself in this position. And on top of all that, MRI is slow. Typically, an MRI scan will last 15 minutes, but it can last up to 90 minutes. And this causes several problems. Of course, we've just discussed the fact that it's very discomfortable, but there are many other things that are associated with this duration. The first is that a lot of people can't access the MRI. For example, you can think of patients suffering from Parkinson's disease or people suffering from claustrophobia who cannot lie still for such a long time. Or you can also think of young babies for which it's impossible to lie still for more than 5 minutes. You also have a reduced patient throughput. What this means is that we cannot prescribe as many MRIs as we would want to, despite the fact that MRI is a powerful imaging modality. And finally, we have an increased chance of motion as time progresses. And the problem is that with motion comes some undesirable artifacts, as you can see here, which render the interpretation of the image more difficult. Therefore, in my thesis, we set ourselves the objective to accelerate MRI scans. And I'm going to show the a selection of contributions that I did in order to achieve this objective in a second time. But in the first time, I will introduce the main concepts that are required to understand my contributions. So they range from magnetic resonance imaging to compressed sensing to deep learning. And after that, I will introduce my contributions, which consist first of a few new networks in the realm of deep learning for MRI reconstruction. And I will show then a technique that allows to accelerate the training of even deeper models. I will conclude then with a wrap-up of my talk and suggest some directions for future work. So let's dive right into the first part of the introduction, which is going to be about magnetic resonance imaging, MRI. So first, let's know what we are talking about. We are talking about an imaging modality, and it's a very versatile imaging modality. You see that here we are able to image soft tissues in different organs, such as a knee and a brain taken from the fast MRI datasets. And those two pictures that you see here actually consist not of a photographic picture, but really we're trying to know the tissue density in each part of the organ of interest. But to know why MRI is so difficult to accelerate, we really need to take a bit of a look into the physics of MRI, and particularly two concepts: the phenomenon of nuclear magnetic resonance and the K-space, which is the signal space of MRI. The first two elements that we need to understand are the main players of MRI. The first is, of course, the scanner, which plays the role of the super powerful magnet, and it creates a very strong magnetic field that we denote here B0. And in this very powerful magnet, we have an organ, here a brain, for example, and what interests us is that the brain is composed of protons, that is represented here by this blue ball. And each proton has a specific physical property, which is a magnetic property, the spin. And the spin, when plunged into a very strong magnetic field, will tend to align with this magnetic field and sort of rotate around it in a precession movement. We can then try to exploit the phenomenon of nuclear magnetic resonance. We are going to send a radio frequency pulse on all the protons in the brain, and by doing so, the spin will be tilted in the plane orthogonal to the B0 magnetic field. This is the first part of the nuclear magnetic resonance, and it's called the excitation. In a second time, the spin will move back up to its equilibrium position in a phase that we call relaxation. And doing so, it will send another radio frequency pulse, here called free induction decay, or FID, that is going to be recorded by an antenna. This is exactly the MR signal. And this MR signal is actually the Fourier coefficients of the anatomical object to image. And therefore, we can simply take this Fourier space version of the image and apply an inverse Fourier transform, or its fast version, the IFFT, to recover the object of interest. And the key part is that MRI is slow because the relaxation is slow. And so it's an incompressible physical phenomenon that we cannot accelerate itself. And therefore, in order to, sorry, before moving on, I will actually try to recap a bit what we've seen. And we know that MRI relies on the nuclear magnetic resonance phenomenon. And this enables us to sample the Fourier space, or K space, of the anatomical object of interest. MRI is slow because relaxation, which is part of nuclear magnetic resonance, is slow. And therefore, if we want to accelerate MRI, what we can do is try to have less relaxations. And what this will give is that this will sample fewer lines in the K space. And so naively, if we use this, we have an undersampled K space on the left. And if we apply the inverse Fourier transform, or the IFFT, we are going to get the following image, which is an aliased version of the image we want to recover in the end. And you can see that this image is blurry and it has an artifact to analyze. What we actually need to do in order to accelerate in a non-naive way is to rely on the concept of redundancy. And redundancy, it has many names. It's also sometimes called sparsity, symmetry, structure, or a priori information. And we're going to see in this talk how we can exploit it and express it correctly in order to accelerate MRI. The first version of which is to simply build more redundancy in the imaging system. And the way we can do that is by using more antennas, or they're called coils, to record the signal. This is a technique that is called parallel imaging. And basically, you can see that it consists in placing different antennas around the object to image. And when you do that, you can't simply then use the inverse Fourier transform, because you have many measurements and you need to use multi-coil reconstruction algorithms such as SENSE or GRAPPA. And I'm going to try to give a bit more detail on GRAPPA in the next slide. So in GRAPPA, the way we accelerate the case space is also by subsampling some lines in it. And what we're going to do is to try to fill those missing lines with a convolutional kernel that is calibrated on a set of lines that are fully sampled. So we use this convolutional kernel to fill out the missing lines in the case space. And then we recompose the final case space using Fourier transform call combination techniques. And this gives us the final image. And this technique is a very good first step into using redundancy in MR systems. But its acceleration when compared to a fully sampled acquisition is limited by the number of coils we have. And therefore, in 2D, it results in an acceleration factor of about 2, which can go up to 8 in 3D. So it's good, but we're not there yet because we still have a very long acquisition scan. And in order to surpass these simple versions of redundancy, we need to use the tools provided to us by compressed sensing. And so in order to understand what compressed sensing is about, I need to frame the MRI problem as a linear inverse problem. But first, let's see what they are about. So typically, a linear inverse problem is going to be an equation of the following form: AX equals Y, where you can think of X as, for example, a smiley. This is going to be the signal we have to reconstruct. And to reconstruct the signal, we have access to a hidden, a smiley with the hidden part. This is going to be our measurements. And what we know is the link between the signal to reconstruct and the measurements. So for example, this is going to be this masking bit under the smiley. And we call this the measurement operator or forward operator. And the problem with this equation arises when there are multiple solutions. And this is the case here. Formally, this means that the kernel of A, the measurement operator, is non-trivial. And in order to select only one of these multiple solutions, we need to use a priori knowledge. So if we take another look at what redundancy means, we know that it's not always strictly equivalent. And for example, we know that for a given measurement, so for example, here, this hidden out smiley, the first 3 smileys on the bottom, starting from the left, are potential good solutions, and they all correspond to these measurements. And we know that the last one for sure isn't the solution to this problem. It doesn't look like a smiley at all, so we know that it's not the solution, and for good reason. It's something that I've drawn myself, and so it can't be an actual smiley. And what we do actually when we sort out between these solutions is that we rely on a visual function which takes as input the image of something, potentially a smiley, and gives us as output a number which tells us whether this whether this image is smiley-like or not smiley-like. And this function is what we call the prior. let's see how we can apply this now to MRI. So in MRI, the inverse problem becomes the following, where X is the 2D or 3D MR image, which is complex valued. Y is the set of k-space measurements for each coil. And the measurement operator is now a compound operator, which regroups the sensitivity maps per coil and the Fourier transform on the omega set. So omega is the trajectory in which we explore the Fourier space or k-space of the image. And it's called Cartesian when it's on a uniform grid and non-Cartesian otherwise. And basically, S, you can think of them as how each coil sees the anatomical object image. And so to illustrate this, you can think of like each element as being, for example, X is the brain, Y is the set of measurements that are potentially undersampled, and the measurement operator represents our knowledge of the physics of the problem. And to solve this inverse problem, we rely on a proxy optimization problem, which is composed of two terms. First, a noisy data consistency. That is, we allow for the measurements to feature some noise, here additive white Gaussian noise, and a regularization term, which is basically the opposite of the prior. The bigger this regularization, the more unlikely the image is going to be an MR image. And to build this prior, we used a wavelet basis. And what you need to know about this operator is that it is a handcrafted linear operator. If we use the techniques provided to us by compressed sensing, we have an additional acceleration factor on top of parallel imaging of 1.5. So we are having some gains, but we know that the prior expressed by the wavelet basis or any other basis is limited because it's handcrafted and linear. And in order to surpass this, we're going to need another set of tools. So let me do a quick recap. So we know that MRI is slow because of relaxation. And we can use redundancy in many forms to reduce the amount of samples we need in the Fourier space and therefore the number of relaxation. But so far, we are limited by simple forms of redundancy. And this is why we're going to move into the space of deep learning to understand how we can use more complex forms of redundancy. And actually, we want to use deep learning because it's a quite powerful tool. Indeed, in our case, the prior is a complicated visual function. And we know that deep learning has been used to build such complicated functions before. For example, it has been used to build functions which can take as input the image of a dog and output a string that just qualifies this image, in this case, dog. And this function f theta is what we call the neural network. It is a chain of elementary, linear, and non-linear functions. We are going to calibrate this function using the framework of supervised learning, where we have access to a data set composed of inputs, such as like the images of dogs, and labels, such as the strings that say dog. And what we want is that the output of the neural network is as close as possible to the prescribed label. And to really express this notion of closeness between the output of the neural network and the label, we use a loss function that we are going to sum over the whole data set in order to make sure that the output of the network is as close as possible to each label corresponding to each input. And we are going to minimize the summed loss with respect to the parameters of the neural network. To do that, to do this minimization, we need to use two main tools. The first of which is stochastic gradient descent, which is an algorithm to solve the previous optimization problem using first order derivatives. And the second one is the chain rule, which is basically a property that allows us to compute easily derivatives of compound functions, which typically neural networks are. On top of that, we actually need a bit of logistics. So in order to train deep learning models, we need a lot of data. We need some compute and memory. So basically all the GPUs that we can get. We need a development framework to code the neural network. And we need to somehow accept that the function that we are going to learn is going to be a black box or some kind of a black box. So if we recap everything we've seen in the introduction, we know that MRI is slow because of relaxation. If we want to do fewer relaxations, we need to exploit some redundancy in MR images. But this redundancy is not easy to express with handcrafted linear functions. And that's why we want to use deep learning, which enables the calibration of complicated functions. Now, I will move on to the second part of my talk, which is related to my contributions in accelerating MRI. And the first of which happened in the realm, of deep learning for MRI reconstruction. And so if we want to apply deep learning to MRI reconstruction, the first very naive way is to simply throw away everything we've just seen so far and to actually frame the MRI reconstruction problem as a supervised learning problem, where the input of the neural network is the case-space measurements, and its label is the image we want to reconstruct from it. And this approach has actually a lot of cons. So for example, it's not taking advantage of our knowledge of the physics of the problem. So we know something about the problem. We could try to use it to build the neural network. And it doesn't scale well. So this type of approach typically only works for 2D data, and it's going to be single code, but it doesn't scale much more than that. What we can do actually is to use our knowledge of the physics of the problem. For example, using the adjoint operator of our measurement operator, here A transpose, to build a more informed model. And the first option is to build this model in the case space, so to try and make sure that our neural network is going to fill out the missing parts of the case space. And then we use the adjoint operator to go from this filled-in case space to the image to reconstruct. Another version is simply to use a deep neural network in the image space, and we can use the adjoint operator to recover an aliased image, like we've seen before. And the goal of the network is now going to be to remove the blurring and the artifacts that are associated with this undersampling. But we can do better than that, right? Because we can try to mix the two previous single domain approaches. And to do that, we have access to a principled method, which is called optimization algorithm unrolling. And so if we take a look at graphical representation of E star, which is the algorithm that is used to solve the canonical MRI optimization problem, we see the following thing where we have two steps. So we have first a data consistency step, and secondly, a proximal step, which whose goal is to minimize the regularization part of the MRI optimization problem. So this is what I've called them here. And actually, what's going to happen is that we're not going to perform this algorithm for an infinite amount of steps, which is the case in theory. But we're going to do it for a fixed number of iterations, big N. And so you see here the representation that we would have if we were to enroll this algorithm for a fixed number of iterations. And the idea of optimization algorithm unrolling is to replace the proximal step of this optimization algorithms with a neural network. And so this is exactly what we would have here. And the particularity of this method is that we are trying to, we train the network as a whole. That is, we do not train each sub-network F theta independently. We train the network end to end. And this is where we had our first contribution. And the goal of this first contribution was to benchmark different unrolled models that are obtained based on the unrolling of different optimization algorithms, different F thetas, and different choice of a number of iterations, big N. And so the results of this benchmark gave us a clear outcome, a clear best competitor, which was the primal dual net. And you can see that in image quality, it outperforms all the other networks. And this was done on 2 data sets, so the fast MRI data set, whose results you see here, and the OASIS data set. And what we did to evaluate those networks is that we simulated the acceleration of MR images, and we trained the network to reconstruct the original data from these accelerated versions. And these quantitative results can actually be verified qualitatively, because let's not forget that our goal is actually to have a very good visual quality in the images that we reconstruct, and not only a good quantitative image metric. And what we can see here is that it's difficult to notice the difference between the image quality just by looking at the images themselves, and we have to look at the bottom row, where we see the error map between the reconstructed images and the reference image. And what you can see is that the PDNet's error map is the flattest, indicating that it doesn't do a lot of errors. If you want to reproduce the results of the benchmark or otherwise extended, the code is available online on this public GitHub repository. And all the model weights are also available online on the Hugging Face hub. We then decided to extend this benchmark to a more challenging acquisition setting, that of 2D multi-coil. And this is where we introduced the Ncpd, which built on many different state-of-the-art techniques in computer vision and MRI reconstruction. So let's take a look back at our graphical representation of unrolled algorithms. So we know that we have this sequence of a data consistency step and proximal step with a neural network. If we group each of those pairs into a single block that I call here the iteration unit, we can try to zoom in and see what's actually happening inside. And now that we have a better view of what's happening, let's take a look at each individual component that is going to be changed when transforming this neural network into an Ncpd net. The first part is that we are going to remove the residual connection stemming from the data consistency and replace it with a concatenation operator. When doing so, what we are doing is that we are not minimizing the data consistency and the regularization term separately. We are actually minimizing them at the same time. The second part is that we're going to replace the convolutional neural network, so the vanilla convolutional neural network, with a more modern neural network, which was at the time of the design of this network the best denoiser available. Finally, what we are going to do is that we are going to add in a module that refines sensitivity maps. Indeed, when I talked about sensitivity maps, I didn't say that they are not a given, they have to be computed from the data. And in order to have an even better computation, what we can do is add this sensitivity maps refinement module. And so the Ncpd was our second contribution, and it was trained on fast MRI data. And I used the Janzé supercomputer to train this data. So the Janzé supercomputer is actually the most powerful supercomputer in France. And after training it, we participated in the Fast MRI 2020 Reconstruction Challenge, where we managed to achieve the second spot. Sorry. And the particularity of this challenge is that it was evaluated by radiologists. And so it was not only based on a quantitative evaluation, but really experts in the data and what we can see for very of the original image. And you can see that it's much better than the algorithm in scanners, so which is GRAPPA. One point I want to highlight, though, is that while it may be difficult to see here, there is a lot of there are instances of blurring and smoothing in the reconstructed version of the XPDNet. And so it is not yet fit for a clinical application. However, we also try to stress test the XPDNet and test it in a prospective acceleration, which is clearly out of distribution. And the reason it is this test was out of distribution is because the brain we are trying to reconstruct has a different orientation than that was present in the training set. It has a higher resolution, a higher field strength, a lower acceleration factor, and it features a cerebellum which was not present in the training set. And what you can see in this figure is that it is virtually impossible to distinguish between the version that is reconstructed by GRAPPA, which is typically what you would obtain in a scanner, and the version reconstructed by the XPDNet, despite the fact that we are talking about a prospective acceleration and an out-of-distribution brain. And in particular, you can see that this is also true in the cerebellum region, which again was not present in the also to the even more challenging setting of non-Cartesian acquisition. So first, the main reason is that they better cover the K-space. You can see two examples of that. So first, on the left, you have a radial trajectory, and on the right, you have a spiral trajectory. And you can see that these sampling trajectories of the Fourier space are not located on the uniform grid anymore. And therefore, we cannot use the vanilla Fourier transform. We have to rely on a different operator, which is going to be the non-uniform Fourier transform. But its simple version is too costly, and we need to rely on its fast approximation, the NUFT, which we implemented in TensorFlow and is available online on this public repository. So let's see how we can transform an unrolled model into an Ncpd and the Ncpd is the network that we use to reconstruct non-Cartesian data. And so basically what we do is that we take all we've designed for the XPDNet, except the MWCNN, which is a bit too complex for this use case. And what's the main innovation of the Ncpd is actually to use density compensation weights, which are there in order to compensate for the fact that non-Cartesian trajectories typically oversample some parts of the K-space. In particular, they oversample the center of K-space. And this was our third contribution. And in this work, we implemented an ablation study to really measure how necessary the the density compensation step was and different parts of the network. And what we saw, and you can see in this figure, is that on all different metrics and for both trajectories, the Ncpd is better than all the other competitors of this ablation study. And you can see that here visually as well, where you can see that all the different networks struggle to remove the artifacts created by radial undersampling. So you can see the streaking lines here in the zoom. And you can see that the Ncpd does a very good job at removing such artifacts. We also extended the study to the 3D reconstruction case. Well, now the difference between the Ncpd and its next best competitor of the ablation study is even more significant. And visually, this translates into this kind of differences where you see that the Ncpd is able to recover a structure in the brain that is blurred out by the unit. So let's recap what we've seen so far. So we've seen that MRI is slow because of relaxation. And if we want to do fewer relaxations, we need to exploit some redundancy in MR images. Deep learning allows us to express more complex structure in MR images than compressed sensing. And we showcase two instances of unrolled models, which are deep learning models, the XPDNet and the Ncpd, which both perform really well in challenging acquisition settings. But what I didn't tell you is that we needed to trade off some model capacity for memory. in the case of training the Ncpd nets in the 3D single coil case. And one can only wonder how this will fare when going to multi-coil in 3D. Or we could also say that maybe it's possible to have even better performance in 3D if we were able to build even deeper models. And this is why I want to move on to the last section of my talk, which is going to be on how to build even deeper models. But the first question we need to ask is, do we even need to build deeper models? And the classical empirical gist of deep learning is that with deeper models comes better performance. This is often caricatured by saying that basically deep learning designers are just people who stack more layers on top of each other to achieve more performance, but actually there is some truth to it. And you can see in this figure by the previous winners of the FastMRI 2020 challenge, the FastMRI 2019 challenge, sorry, that if you add more unrolled iterations to your unrolled model that are called blocks here, you will get an improvement every time. And so it means that empirically we also observe that deeper models give better results in MRI reconstruction in particular. Another question we need to ask is, can we go deeper? The problem is that with deeper models also comes an increased requirement for training. And the memory we have for training is typically constrained. We need to train those models on GPUs, and they have a memory which is going to be typically of 32 gigabytes. And in order to understand how to alleviate this problem, we need to understand where does this memory requirement come from. And counterintuitively, it doesn't come from the model size itself. Most of the time, it comes from the activations. So what are activations? Let's give a simple example. So if we consider this intermediary function here, whose input is x and whose output is y, and parameterized by theta, when doing the stochastic gradient descent, we need at some point to backpropagate the gradients from the output of the function to its input and its parameters. Basically, we need to be able to compute those two gradients here with respect to the parameters and with respect to the input. And in the expression of those gradients, when you derive it, you see that y appears in this expression. And y is exactly what we call the activation. We need to store it in order to accelerate the computation of the different gradients that come into play during the backpropagation. And so, of course, there are different many modeling solutions besides simply trying to use bigger GPUs with even more memory. So the first two that I'm showing here, so gradient checkpointing and invertible networks, are solutions which still rely on activations, but they store them in a different way. And the third one really uses a different paradigm. So implicit models do not rely anymore on activations. And this is why they're interesting. And this is why we're going to focus on them today. In particular, we're going to focus on a specific type of implicit models, which are deep equilibrium networks. In deep equilibrium networks, the output of the network is no longer given by a chain of elementary function. It is now given as the solution to a fixed point equation. In practice, we solve this fixed point equation using a quasi-Newton method simply because the fixed point equation is actually equivalent to a root finding problem. But now, because we don't have this chain of elementary function, we cannot rely on the chain rule anymore to compute the gradient of the loss with respect to the parameters. But we have access to another tool, which is the implicit function theorem, which gives us exactly the gradient of the loss with respect to the parameters in a closed form fashion. And in particular, this expression does not rely on activations. So it means that we can perform essentially memoryless training. And so these networks perform great in like actual applications. So for example, in language processing or in computer vision tasks. And you can hear on the image classification task on the Cypher-10 dataset that's deep equilibrium networks, in particular here their multi-scale version, as classes. The only problem is that you can also see in this figure that the memory required, the time required to train them is actually up to 2.7 times more than, for example, the case of the ResNet. And so basically what we're saying is that these models are slow to train. And to understand why they are slow, we need to recall the computation of their gradients, and in particular, highlight that we need to invert a huge Jacobian matrix in a certain direction. And in practice, this is done with an iterative algorithm, which takes time. What we proposed in our last contribution is to the Shine method, where we approximate the true Jacobian inverse with a quasi-Newton matrix. And this quasi-Newton matrix B has a few key properties. The first is that it is computed when solving the root finding problem associated with deep equilibrium networks. So it basically comes for free. And the second is that it is easily invertible using the Sherman-Morrison formula. So we don't have this problem of the hardship of inverting this Jacobian anymore. And this method is actually very versatile because it can be applied in other settings than DEX. And in particular, it can be applied to hyperparameter optimization. Specifically, it can be applied in this setting if the inner problem can be solved using a quasi-Newton method. And this is typically the case when the loss is a logistic regression loss. And so to evaluate our method empirically, we evaluated it first on this hyperparameter optimization problem, where we used the logistic regression loss. And we looked at the performance on a held out test set. And what you can see in this figure is that our method Shine is able to outperform its competitor in terms of convergence speed on this held out test set. Moreover, this allows me to introduce the refined version of Shine, which is basically a way to smoothly transition from the approximated matrix to the correct Jacobian inversion. And we then empirically evaluated our method also in the context of deep equilibrium networks. Here in the case of two data sets, first a small scale data set, which is Cypher, and then a second bigger scale data set, ImageNet. And the main takeaway of this figure is that we are able to accelerate the training of deep equilibrium networks using Shine, although it is a bit anticlimactic because we perform as well as the other competitor method, the Jacobian field method. I just want to recall that the Jacobian field method is not able to accelerate hyperparameter optimization. The second takeaway of this figure is that the refined method allows us to trade off some model training speed for some final performance. We see that here the performance drop is not very significant, but we can still trade off this minimal performance drop for some computation time using the refinement. I will now conclude on this whole presentation. So I will recall a few things. So we've seen that MRI is an important medical imaging modality, but it is inherently slow due to the nuclear magnetic resonance phenomenon it relies on. Using redundancy is our main thing. Redundancy is not always straightforward. In a more principled way, and we saw two examples of this. The first is the Xpd net, and the second is the Ncpd net, and they both perform really well in challenging acquisition settings. Finally, in order to prepare for even deeper networks with the promise of even better results, we proposed Shine, a method to accelerate deep equilibrium networks, which are memory efficient models. I will now suggest some directions for future work. So the first is, of course, to simply apply these deep equilibrium networks to MRI reconstruction. The second one is actually to refine the measurement operator even more than simply refining the sensitivity maps, for example, including some B0 field inhomogeneity corrections. Also, because the Ncpd net is fully differentiable, we now have a tool to learn the acquisition trajectories rather than simply saying that they are fixed, such as radial or spiral trajectories. We can learn them. And finally, we can also use the Ncpd net to reconstruct different MRI modalities, such as fMRI, which is a 4D modality. It includes a time component. Before concluding this talk, I also wanted to mention some additional contributions that I had during my thesis. So the first of which was the LearnLess, which is a wavelets-inspired network. And the second of which is the application of denoising score matching, a recently introduced technique, to MRI reconstruction in order to obtain uncertainty quantification. I also had some contribution in knowledge dissemination. I co-founded the Janzé user documentation, and I also co-founded a Neurospin deep learning lecture group. I want to end this talk by saying a big thank you to all of you. So it's been an amazing 3 years, despite the fact that it's been quite rocky. Indeed, at the beginning, we could be freely roaming on planet Earth and playing paintball. And at the end, we had to take group pictures on Zoom. So it was very different from the beginning to the end. But I still want to say a big thank you to all of you. Thank you for listening to my talk.
Okay, thank you. 44 minutes. So now the questions. Let's start with the Benjamin. Yeah, okay, go ahead.
So, thank you very for the presentation. I really like it, especially the beginning of the introduction, because it really helped for me to know what to expect from the methods. That MRI was slow, so you expect from your method to accelerate the process. So it was helpful for me to but I mean, I have slide by slide maybe comments so that you can.
So we can do the feedback after, but like let's first now do the questions as you would if you were part of the jury.
Yes, okay. So in the beginning, you mentioned that in your benchmark projects, you compare the architectures and also the number of iterations you need for your Unrolled method. But I mean, I was curious how you compared the number of iterations you need. Like you didn't mention that, I think. So, like, did you have a strategy to compare this parameter?
So unfortunately, no, I didn't do a benchmark that was so extensive. What I did was basically to take 3 different networks that were present in the literature. And these networks had a set amount of Unrolled iterations. And so I don't know how each of these networks set their number of iterations, but what I can say is that they probably basically tried to have the biggest network possible for their GPU requirements. But so in this benchmark, it was not a benchmark where I selected all the possible algorithms to enroll, all the possible choices of f theta, and all the possible ends. So I didn't do this this benchmark in this first contribution.
And so in the Unrolled methods, in the slide you showed us, you had a different set of parameters theta for each iteration.
Mm-hmm.
So I was wondering if you're first optimizing the methods and then applying this Unrolled algorithm to your data, or you put the joint optimization.
So yeah, so really here what we're doing is, so indeed we're using different sets of parameters for each proximal step. So this is an architectural choice, and basically here I'm trying to stay as general as possible, but it's definitely possible to have the same theta in each subnetwork. When we have different theta parameters in each step, we are learning the network end to end. So we're not learning each f theta function on its own on a separate problem, like for example, using the denoising score matching technique. So we're not doing that here. We're really learning it in an end-to-end fashion. And what I can say about the choice of using a different f theta versus the same theta is that when you use the same theta, basically you're removing some model capacity. And so this is some kind of regularization. But of course, if you use the same theta, then you have different options as to how you want to train the subnetwork and how you want to apply the network itself as well. Because when you have the same theta, you can increase the number of iterations or decrease it at inference time.
I have a next question. So you mentioned that the main advantage of deep equilibrium models was the saving memory.
Mm-hmm.
But that the limit of GPUs, is there another advantage of uptake of this implicit model?
I don't think so. Right, that doesn't come to mind straight away. So yeah, like with an infinite amount of memory, like I would say it's a difficult question to answer. So like for now, I would say no. I think like the main advantage is that it's memory less, and this allows us to build deeper models. But yeah, I don't see it.
So thank you for the presentation. Maybe I had one question about also about the benchmark. So you benchmarked several different architectures, and would you have any like key takeaways on? I mean, I guess this architecture can share some parts in some sense, and so benchmarking all this architecture, were you able to do some kind of ablation study to see what was the like really important part and what was the part that are like less important in all these networks?
Unfortunately, no, I didn't do it myself. But there exists different benchmarks that are tackling such a thing. So in this case, it was just simply saying there are networks that have been proposed in the literature, but they have not been compared together on the same data set using the same metrics, using the same code base. So this was purely this job here, which was not to do an ablation study, but this ablation study has been performed then by different people. So I showed the work of Pezzotti and colleagues, the winner of the 2019 Fast MRI Challenge. But the runners-up of the challenge also performed an ablation study on different components of unrolled networks. Unfortunately, like these studies are already a thing of the past because new components have been added and which have not been studied in these benchmarks. I think one of the takeaways still that I got from this, like training the networks and not doing a proper ablation study, is that it is not necessarily a good thing to have a very deep, a very big F theta network, and it's better to allow for more unrolled iterations. If you have to choose between the two, it's better to trade off and pick more iterations than pick a big F theta model.
Okay. This seems like really like the core idea of comparing all this is really like finding like the components. Like for instance, I mean the question of like sharing the weights, is sharing the weights better or not? I feel like it's.
Yeah, so in this study, I didn't do it because like all of these
had
different weights. So basically, what I've seen in the literature is that when you have a reduced size data set, it is better to share the weights. And so this is basically why I was saying that it's I regard it as a regularization strategy. It's because really in limited data setting, it's better to share the weights simply because you're going to have a lot of regularization. But if you're in this case of the fast MRI dataset or this other dataset, which was Oasis, where you have a lot of data, then in this case, it is going to be better to have different weights because you won't have like such a deep model that is going to overfit your data. So far, like with these kinds of models, I couldn't overfit on the fast MRI data.
Okay, but the question to this question, but the point is how much you gain by not sharing in terms of because it's you can always say I need more GPU, more memory, and everything, but what is the gain at the end compared to sharing?
Okay, so I don't have a number to give, unfortunately.
Because if the gain is 0.1%,
yeah,
I would say you should share.
So I don't have an answer for that, but it is not 0.01%. It is more in the orders of like 0.2 or 0.3 dB. But like this is not something I'm going to like put my reputation on because I didn't do the proper.
It's 0.3 dB. Okay. So from the legal point of view, that's worth it to spend this amount of time and burn GPU time.
I mean, like the thing is, sharing the weights or not sharing them is not going to have an impact on the GPU time or the GPUs themselves. So it is just because like when you use the parameter sharing technique, basically you have access to different training techniques, but these different training techniques, they're not going to necessarily give the same as an end-to-end training. And this really I have not seen a comparison between training the subnetwork offline and training it end-to-end. So
when you said sharing is you have the same network at every unit, right?
So when I call
right?
Yeah. So when I say weight sharing, for example, it could be the similar thing where you have the whole network trained end-to-end, but it's just that the f theta i's are all equal.
Okay. So another question in consideration now. I just tried to think about the practical part of it, right? Being I don't know, working this way. So you know that if you have enough data, you can afford not to share.
Yes.
But you know the ratio of data and units, at which point you say, okay, I can afford not to share. At which point you say, oh, now I should be cautious and share my parameters.
So unfortunately, I don't have an answer for that. I didn't perform this ablation study either. There are a lot of ablation studies that are needed to really understand the depth of these networks. But like the first thing to know is that they are like the conclusions that you can draw in simple settings, for example, 2D single coil, are not necessarily going to be the conclusions that you draw in much more advanced settings, so multi-coil, 3D multi-coil. And so if you want to do exact conclusions, you have to perform these expensive ablation studies in different settings. So now this is the context to answer your question. I didn't perform this ablation study in the context of unrolled models for MRI reconstruction. So basically, like the learning curve of MRI models on this fast MRI data. It is possible, and what I think you would see is that at some point the lines cross, and it is better to have more regularization when you have not a lot of data. But a lot of regularization techniques are actually possible, and weight sharing is only one of them.
And then the second one is, sorry, I just took time for the question.
No, don't worry.
Because it's the same question that I want to say on this. Now you also show that if you add more units, then you will still improve the result.
Yes.
And the question comes at the end is it better to add units or to not share the parameters? Because more you add units, this is actually a very good one.
So this is, I think this is one of the points that I really want to dig into after my thesis. I think this point is super interesting. Are we actually learning something that is more than simply learning a prior and its proximal step? And this is why you would want to have something which is shared, or are we just accelerating this learning? Are we just learning how to take shortcuts? And this is something I think it's a very deep question. I think you can also think of it as like, because what we're doing here when we're concatenating rather than subtracting, what we're doing here is that we're also shifting from a paradigm where we optimize alternatively the data consistency and the proximal operator, so and the regularization term, to a paradigm where we minimize both at the same time. But this is only theoretically, but maybe we're doing something even more than that, where maybe it's not even a question of minimizing both at the same time. Maybe we're like going beyond the Bayesian, let's say, view of this. And this is something that I think nobody has tackled yet. And it is not only present in these PDNet architectures, it is also present in another set of architectures, which is called the recurrent inference machines, which have been introduced by Petsky and Welling. And basically what they do is that, like I said, they generalize from updating alternatively the proximal operator, so here the log of the prior, and the data consistency, so here the log of the likelihood of the data consistency, and they generalize it in minimizing at the same time. And so I think that it's really key to understand whether this generalization helps us just to accelerate or really to learn something new. And I think it's a question that cannot be answered simply by doing empirical validation, because we can always try even more, and maybe we're not at the right amount of iterations to reach convergence. So I think it's a really I think it's an extremely deep question. But, yeah.
Okay, go on. Yeah. No, but I mean, I think there is something important with weight sharing that is that you cannot achieve with non-weight sharing, is that if you go to infinity with the number of layers, then you recover this the fixed point equation, and all these decks are using this fixed point equation, and you have this weight sharing. So I think it's important, and the answer of like weight sharing or not weight sharing depends a lot on n, the number of layers. And so if you go to infinity, and it's what we showed with Theorem, with the paper of Norris. If you go to infinity with the number of layers, asymptotically, you cannot learn anything better than just using the softmax and using the right weights. But if you are before, then if you have a limited limited computation, then not weight sharing is interesting, because what you need, this is a kind of link to with the homotopic method, or like you don't need the same regularization at the beginning and at the end, and you can learn this by not sharing, actually. And you can go faster at the beginning and then go a bit. So I mean, this is like, I think it's a really deep question. I agree. It's interesting to it would be interesting to. I had a second question, which was about the XPDNet. I think my question was which the most critical to change to find a good like how much time did you spend to design this new network from the PDNet? Okay. What was like really like the key points that that you, if you had like one chance to do from PDNet to go to XPDNet, which one would be the most important part?
So from PDNet to XPDNet, there are only two changes. So it's only the sensitivity maps refiner and the denoiser. So I think so. What happened is that I didn't do a proper ablation study where I removed both at the same time. What I did a lot was try to understand which was going to be the subnetwork that I should use to represent F theta. So I performed basically a benchmark. So this was an informal benchmark. That's why I didn't publish it. Where I implemented a lot of denoisers as a denoiser on its own, and also which one gave the best performance when embedded in the PDNet. So unfortunately, so far the results have not been what I expected, because there is not a strong correlation between the results you have as a denoiser and the results you have when embedded in an unrolled architecture, which is disappointing, because you could think that it's possible to basically predict what you're going to get. So I think that really it's critical to pick the right architecture here. And this refiner module, to be honest, I haven't tried like very simple refiner modules. And I think that here, for me, it was more a question of the simplicity of this approach compared to like having this big manufacturing before of trying to design the perfect sensitivity maps. It was more a question of like, this is going to be super simple. I can have coarse sensitivity maps and just learn them. So I would say that it's really here I spent a lot of time trying to pick the the MWCNN.
Okay. All right. And my last question for you is for the text. So you applied it for Shine actually. You applied it for hyperparameter tuning and on this image specification task. And why did you not try to implement it for MRI?
So I actually tried to implement it for MRI. So not Shine, just Dex first. And so actually the journey was in this order. It was I saw the Dex and I thought it was a really good idea for MRI and MRI reconstruction, and I actually tried to implement them. And I faced a lot of hardships. It's actually quite difficult to move simply from DEX to MRI reconstruction, from DEX applied in classification or segmentation to MRI reconstruction, because there are a lot of things that need to be taken into account. And what happened is that I was debugging this training, and this is where I noticed that there could be an approximation that could help us in accelerate the training. But it was more like serendipity than actually
issue of time and
and also what happened, I don't know if I should say this, but what happened is that one of the members of the jury also was pursuing exactly the same lead, and so at this point we decided to say, okay, we have a good idea, let's pursue that idea rather than doing just another application of the same idea.
Okay. Thank you. That will be my questions.
I have a few questions.
Yeah.
Okay, so this is very nice work, but you're using this type of models which are kind of black boxes, and you're proposing to apply them to some applications that are really critical. And so my question is, how much trust do you have on the images that are produced by these methods that you're proposing, and how do they compare to the previous generation of methods that are worked on Proxy?
Okay, so I think the main question is how do you define trust in this?
As a doctor, looking at cancer cells.
Okay, so again, it depends what kind of doctors we're speaking about. Is it the doctor that is going to expertise the method, or is it the doctor that's going to use the method?
Operate on the patient.
So operate on the patient. I think the first thing
diagnose.
Okay, diagnose. I think the first thing in this setting is to understand that I think that in this case it is difficult to talk about trust for the doctors that are diagnosing such images, because even the current systems, I think, are very complex, and we cannot say we can decently say that reasonably say that most of the doctors that diagnose those images don't understand the full pipeline that allows to generate these images. So trust about it, and what is this case? I think that trust can also be described as just the raw performance. And the problem with performance in this case is that it's very difficult to anticipate the performance for the unforeseen events. And typically, there is going to be always this person saying, what about this tumor that we hadn't in the data sets, in the training data set, or the validation data set? And I think that so far, the way these algorithms have been implemented in the clinic, so maybe what I should say is that the winners of the FastMRI 2019 challenge, so these people, Pezzotti and colleagues, they are a group of researchers from Philips, and actually this algorithm, so not all these ones, but just the best performing one, has been FDA cleared. And it is relatively similar to the XPDNet. It even has less components that make the XPDNet a better performing network than this. And the key aspects of why they got FDA cleared, and maybe this doesn't answer all your questions, but it at least gives some practical insights, is because they're Philips, they are able to perform a lot of scans and a lot of reconstruction using these networks. And the trust comes simply from the fact that it performs well over an extended period of time for a variety of different scans. And I think that so far, so I would say that the conclusion of this is a bit disappointing in that so far the only solution is to have a ginormous data set and say that it works well.
Do you have any way of estimating the uncertainties of your maps, of your reconstructions?
So, like, for now, I haven't built that in the Ncpd. So it is possible to build some sorts of uncertainty maps, let's say, in a straightforward way, but we don't really know what these maps are. But actually, in the application of, in the application of denoising score matching techniques that we did with the members of Cosmostat, we actually showed that it is possible to design deep learning-based methods that produce a lot of samples for the same measurements. And these samples, they do not give us like kind of an uncertainty map, which is difficult to generate, but they actually allow us to see which parts of the reconstruction are constrained by the data, and which part of the reconstruction are, let's say, hallucinated or generated by the networks part of this method.
Okay, so I had another question in the same spirit of what I asked you before. Is there is an elegant solution and there is a practical solution. If the elegant solution is as efficient as a more crude way, then it's good to take the elegant one. But sometimes you take a practical thing which is faster, and you get almost same performance, right? So, for instance, one thing I was wondering. So you have this non-Cartesian Fourier analysis, and you have the same in astrophysics, right? You have some kind of Fourier components, or it can be shear measurements, or balancing, and you can have the option of making drilling, and then using fast Fourier transform, which is extremely convenient, or you can use non-equal space effectively, and then you can multiply by a huge factor. And in practice, very often we like the grading, right? So, so here, I guess it's the same. So using the non-Cartesian Fourier transform, increase the amount of time by a huge amount, I guess.
Yeah.
And you were mentioning that time is important. That it worth it.
Is it worth it? So the first thing I want to say is that we did indeed perform this analysis of looking at whether gridding is the best performer compared to using the non-uniform Fourier transform. And what I want to underline is that we did not use the correct expression of the non-uniform Fourier transform. We used its accelerated approximation, which is called the NUFT. Okay, so this is the first thing I want to highlight. But you can see here that in this apple green, you have the gridded version of the NUFT embedded in the PDNet. And when we use the Ncpd, so with the actual non-uniform Fourier transform and the density compensation, you see that you are performing better all around. And in particular, you can see that on the proton density, so PD contrast, you are much better than the gridded version. So the first thing here is that we are seeing a clear and significant improvement on image quality. And you can also retrieve it visually. The gridded PDNet is not able at all to remove the streaking artifacts that you can see. Now, to answer your question of whether it's worth it, I would say that it's worth it because here the reconstruction times are extremely fast compared to what is currently implemented in the scanners. Even though indeed the gridded PDNet, and I don't have the numbers here in my presentation, is faster than the Ncpd, it is still relatively far from what is done currently on the scanners. And it is nothing in comparison to the whole acquisition process. So the amount of time that we lose on the reconstruction is still very negligible compared to the whole process.
Okay. Yeah, to discussion of offer. So there are some people who are not in favor of deep learning for inverse problems, mainly due to hallucination problems. And also some striking images where you see in the brain some kind of filaments which are completely created by the method. And it's completely shocking to see that the same feature that we are looking for are created by the method. So what do you think about that? And what is your point of view?
Right. So I think it's a very complex question that I haven't taken the time to read into enough in this thesis. Is like when we deploy such models, what is actually needed in terms of validation. So again, like I said, the best way is to simply have as much data as possible, as diverse as possible, and to test your method. I think the first thing is that previous methods were also sometimes generating artifacts. And so these artifacts, they may sometimes be easily brushed off as being anatomical-like, but sometimes they are anatomical-like and they can have some issues. I think that the next point is if in some cases the model allows us to perform even more MRIs, I think it's still a good thing to have something which enables us to have this trade-off compared to not having the possibility of having this trade-off. Here we have the possibility of potentially having super fast MRIs, but like even if there are some hallucinations, we can say that in some cases we want to take some time and maybe have a second let's go a second exam, which wasn't the case before, and now we have the possibility to do these kinds of things. So I think it's an answer in two parts. The first part is simply saying, it's very coarse and brutal, but it's just saying if we want to build trust, we need to test the model over an extended period of time over a lot of data. And if we want to have a model that is not trustworthy but still useful, we should be able to say it allows us to have a trade-off between speed and accuracy, which wasn't present before.
Okay, so I have a last question. So reading your manuscript, I've noticed that you have addressed two main challenges in deep learning, right? Generalization and uncertainty. And you are not presenting during your talk. So is there anything special that you don't like in this method, or? So
really I think the main deciding factor for this, so like I said at the beginning of my talk, I'm presenting only a selection of my contributions. And I think that
you didn't decide to respond to two major aspects of deep learning.
So I think that the what I want to really clarify is that the second contribution, so the uncertainty quantification, is purely applicative. So it is not something that I didn't provide any methodological improvements in this contribution. And the reason I decided to select what I presented over like the learnlets, for example, is simply because it was a very arbitrary choice. But I said, okay, what are the research output that has been accepted and let's say put forward so far, and the learnlets was not part of them. Like even until this point, I didn't receive but it was sent apparently, the answer from the editor. So it was purely this question of like, how do I make the choice? Because I think I could still have it.
I don't want it.
Okay.
Let's see if Denise says.
You have a question?
No, okay. Really, my question was related to what you asked you. Because, no, I mean, the question was that one, because you know, in this kind of image, it's very important when the very small detail can be very important. And so, yeah, my question was how you can trust that your neural network is not introducing important, and so that you're like seeing cancer where there is no cancer. And then I I have another question that is related to the slide 90. Because you say that, but you say that this image is not quite useful in terms of medical purposes.
So I said that it's not ready yet. I'm not saying that it's not useful. I think it's still useful because it allows you to see the big structures. But I don't know, like, for now, what the radiologists have said is that it's not possible to accept this so far, like in this current state.
And
this
you
is,
say that there is, I mean, because you say something about the smoothing that is smooth.
yeah, it is a bit smoother than the reference image.
And the thing is that maybe I saw that I'm seeing the images like more clear than the reference image. I don't know if that can be my impression.
Yeah, maybe I should try.
More smooth than the.
Yeah, maybe I should try to have a zoom and some arrows in them to actually showcase this.
Here, the question, yeah, they say why you are not sure that you're not introducing artifacts, because for me, it's like this image is like more clear than the reference image. Then other things that I didn't understand, the Graphical method is like the algorithm that they use in the normal MRI, or is just another algorithm that your algorithm always when they exploit these values?
No, so it's the algorithm that is actually implemented in MRI scanners, but it never produces such images simply because we never accelerate that much in MRI scanners. It's just that here I'm taking the algorithm to its limits beyond its limits.
Because there are some like structure inside that you can see in the reference image, right?
Yeah, no, it's generating artifacts.
Okay. Oh, okay. Yeah, okay. And then, yeah, another thing that I don't understand was you can compare like the 3D images. I mean, you talk also about these 3D images, but maybe it's a silly question, but I mean, you're still looking at MRI images. So why they are 3D?
So I guess you're talking about these ones. Sorry, these ones.
Yeah.
Yeah. So the reason I'm talking about 3D is indeed because we're acquiring the volume in a 3D fashion. So in the other cases, what we're doing is that we're traversing each slice's Fourier space individually. And in this case, we're not traversing each slice Fourier space individually, we're traversing the whole volume Fourier space. So we have a 3D Fourier transform rather than a 2D Fourier transform for each space. Okay, thank you. I'm going to stop here the streaming. Sorry.